Hello everyone. Today we're gonna discuss the effect of pressure drop on conversion. But before we proceed, I would like to remind you to install Polymath in your laptop. Okay, in the previous lecture we have developed the Ergun equation together, or actually we did not develop the Ergun equation, we have modified the Ergun equation to look like the following two equations so that we can use it easily in the design of reactor. So here we go. This is the first form of Ergun equation written in terms of molar flow rates. This is the second form of Ergun equation written in terms of conversion, and we said in a special case where epsilon equals to 0 and t equals to t naught, we can simplify and solve the Ergun equation analytically to get to this equation. Basically, we want to know how P changes as the reaction progresses. Okay, let's listen to the story of pressure drop and rate. So let's examine the effect of the pressure drop on conversion in a packed bed reactor for second order gas phase reaction with epsilon equals to 0 and t equals to t naught. Obviously, you're going to use the analytically solved Ergun equation to find P as a function of W. So in a case where we don't have pressure drop, no pressure drop, that means obviously it means that the pressure remains constant. So P does not change down the length of the reactor, So as we go down the length of the reactor, W increases, right? And P actually stays the same. Okay, so we say no pressure drop, right? No pressure drop, that means P remains constant. However, we do know that if the flow is going through a packed bed, then there is a pressure drop. The flow experiences pressure drop. And how do we quantify? How do we calculate it? We do that through Ergun equation. So we can calculate actually how P changes as W increases. Okay, so this is the figure now. This is the curve showing how P decreases as W increases. What that has to do with the volumetric flow rate, how that affects the volumetric flow rate. Obviously, when you have pressure drop, the volumetric flow rate increases as you go down the length of the reactor, because as pressure decreases, the molecules become far from each other more and more. Therefore, you have higher volumetric flow rate. If you have a higher volumetric flow rate, that means you'll have lower concentration in a case where you have pressure drop compared to a case where you do not have pressure drop. Okay, and then this obviously affects the rate of reaction. So when you have pressure drop, we'll see that the rate of reaction is lower than a case where you do not have pressure drop. How does the rate law or rate of reaction affects conversion? Obviously, if you have lower rate of reaction, you will end up with lower conversion for the same W. Okay, so now we know the story of the pressure drop and the rate and the conversion. Okay, let's proceed. Analytical solution for reaction with pressure drop. Let's discuss how the pressure drop affects our CRE algorithm. So we said the algorithm, the CRE, chemical reaction engineering algorithm for the design of reactors, consists of 5 steps. And let's consider the second order isothermal gas phase reaction, A goes to B, occurring in a packed bed reactor. So the design equation, this is how it looks like. And in the design equation, we are introducing, or we need the rate of reaction. So that's why we shift to the second step, which is writing the rate law. After writing the rate law, we see that we have introduced a variable, which is the concentration, and we write the concentration through utilizing the stoichiometry. So here we go, Ca equals Fa over epsilon, and of course you know Fa equals Fa naught 1 minus x, and epsilon equals epsilon naught times the 3 correction factors. After manipulation and simplification, we get this equation. After writing this equation, you see that you have another variable, y, which is P over P naught. And this is a variable because P decreases as you go down the length of the reactor, right? So now we have introduced a variable, therefore we need to provide an equation for, and that equation would obviously be the Ergun equation. And this is the Ergun equation in a case where you have isothermal operation and epsilon equals to 0. Okay, let's combine all the 4 equations together into one equation, and we get this equation. Can we integrate? Yes, we can. All what we need to do is to separate the variables. So let's separate the variables and let's integrate using the appendix, which I'll leave you to do this at home. And here we go. We get an equation which relates conversion to the mass of the catalyst inside the reactor. Okay, we can solve for x to get this equation, and we can solve for w to get this equation. However, with the help of solver, we don't need to actually solve for these equations, but it's good to have. Okay, so we have these equations, which remember that's only applicable for isothermal packed bed reactor with pressure drop for second order gas phase reaction with epsilon equals to 0. So this is not an equation that we will memorize. Okay, so now we have taken into consideration the effect of pressure drop into the design equations. Okay, example 4.5, effective pressure drop on the conversion profile. Reconsider the packed bed in example 4.4 for the case where a second order reaction, A goes to B, is taking place in 20 meter of 1.5 inch scheduled 40 pipe packed with porous catalyst. The flow and packed bed conditions in the example remain the same, except that they are converted to metric units. That is, P naught is atmosphere, so we have it in SI units. T naught, we have it. The length is not 60 feet anymore, it's written as 20 feet. The particle size is given, the temperature is constant, given epsilon naught, the volumetric flow rate is given at the entrance. K for the reaction is given. The pressure drop parameters beta naught is calculated, remember in example 4.4, but now we convert it to kilopascal per meter. The cross-sectional area is given. The solid catalyst density rho c is given. The void fraction is given as well. Right, so what do we need? First, calculate x and neglecting the effect of pressure drop. So this reaction is taking place in a packed bed, and I know that in a packed bed we do have pressure drop. However, for simplification, we neglect the effect of the pressure drop, and then we need to calculate X accounting for the pressure drop. And then there is a third requirement we're going to talk about later. Okay, let's start with the first requirement, which is calculating X neglecting the effect of pressure drop. How do we solve this problem? Obviously, you'll need to start with the design equation, right? You need to start with the design equation, and after that you write the rate law, and then you utilize the stoichiometry. And obviously here you consider T over T naught to be 1, and also you consider P naught over P to be 1 because you're neglecting the effect of pressure drop. Once we combine all of this, then we get this equation, which is easy to integrate to get this equation. Now we want to calculate X to the given W. First, we need to calculate W. Obviously, we have the density of the catalyst, we have the void fraction, we can calculate the density of the bulk density, we have the volume of the pipe where it is packed with this catalyst, so we can calculate the mass of the catalyst. So go ahead and calculate the mass of the catalyst after calculating the bulk density. Okay, so here it is. So this pipe, which is 20 meters long, which is packed with these particles, where the particle density is given and the void fraction is given, therefore the packing density is this much. So this pipe actually holds up to 27.5 kilogram. Okay, let's find some other parameters and let's calculate X. So X in this case is 82%. So the expected conversion out of this packed bed, where this reaction is carried out at this temperature, which has this K value, rate constant, and the given rate law, second order rate law, would lead to a conversion of 82% if the pressure is neglected, if there was no pressure. However, in reality, we know that there is pressure. Means we need to take into consideration the pressure drop. How do we take into consideration the pressure drop? Of course, we use Ergun equation to account for the pressure drop. Okay, so for the isothermal packed bed reactor with the pressure drop for second order reaction with epsilon equals to 0, which we just solved together, right? Before this example, we solved this design and we got this equation, correct? Okay, so we got this equation. Now we can calculate alpha from this equation, and the value of alpha is given as 0.037 per kg. This is the pressure drop parameter. So we have two pressure drop parameters in Ergun equation, and the modified form of Ergun equation. We have the alpha and we have the beta naught. Beta naught basically it's a property of the bed and the flow at the entrance, and alpha depends on some other parameters like beta naught, P naught, cross-section area, and the bulk density. Okay, so we calculated alpha. Actually, the alpha is some value per kg of packing. So that means if you have higher values of alpha, that means you'll have more pressure drop per kg of packing. Okay, so beds with higher alpha experience, or the flow experience, higher pressure drop. What about if you don't have pressure drop? Then what happens to the value of alpha? Yes, correct, the value of alpha would be 0. No pressure drop, that means alpha is 0. If we put alpha equals to 0, obviously we go back to the original equation in part A. So maybe it was easier to start with part B and then you solve part A as a special case of part B. No pressure drop, no alpha. Okay, anyway, let's go back to our case, and where we have the design equation solved and evaluated. In the case we have pressure drop. Now let's calculate X. Okay, so the resulting X is only 69%. Why is that? Why, when we have pressure drop, the conversion is lower? You know that answer, right? You know the story of pressure drop and the rate low, right? Because when you have pressure drop, the pressure decreases down the length of reactor. So you operate at lower pressures. When you operate at lower pressures, that means you'll end up with higher volumetric flow rates, right? Higher volumetric flow rates will lead to lower concentrations inside the reactor. Lower concentration leads to lower rate of reaction. Lower rate of reaction will lead to lower conversion for the same mass of catalyst compared to a case where you do not have pressure drop. Okay, now let's discuss the final requirement. That is, determine how your answer to B would change if the catalyst particle diameter was doubled. So what happens if dP was doubled? Assume that the rate constant K is unaffected by particle size. An assumption we know from chapter 12 is valid only for small particles. Okay, so let's assume that K does not change as we increase dP. This is only an assumption, which is true for small size particles, right? Okay, so let's double the particle size. What do you think would happen? Okay, let's look at a schematic plot. Okay, in this case, I've drawn that duct as a square duct. However, you know that we have a pipe, just to make my drawing simpler. Okay, so we doubled, right? We doubled the particle size. What do you see? Well, obviously, I did not change the void fraction. The void fraction is the same, because although you have here larger voids and here smaller voids, but here the number of voids is more, right? So the total void fraction remains the same, but the void between the particle increases. What happens when the void between the particle increases? When the void between the particle increases, the resistance to flow decreases, correct? Imagine you are blowing in a small pipe and then you're blowing in a bigger pipe with a bigger diameter. Which one is easier? Obviously, when you blow in a straw which has larger diameter, it's easier than blowing in a straw which has small diameter, correct? So when you have the void, when the particle size increases, the void between the particles increases, so that you have less resistance to flow. Resistance to flow means less pressure drop. So if you have less pressure drop, that means you maintain higher pressure. That means you maintain lower volumetric flow rate, which results into higher concentration, which results in higher rate of reaction and therefore higher conversion compared to the case where you have smaller particle size, correct? Okay, how all of this is reflected into my equations? Obviously, it's reflected into, let's see where the particle size appears. We found it. This is the particle size. It appears here. Okay, and therefore, the value of beta naught changes with the doubling of the particle size, and therefore alpha changes as well. But let's remember the value of this term was only 300. The value of this term was around 13,000 because the flow is turbulent, and this is dominant. This term is dominant. So let's neglect this term. Let's neglect this term compared to the other term. And now we see that the beta naught is inversely proportional to the particle size, right? It is inversely proportional to the particle size. So beta naught is inversely proportional to the particle size, which means that beta naught in case 2 divided by beta naught in case 1 equals dp in case 1 divided by dp in case 2, correct? Because there is reverse, they are reversely proportional. Okay, do we have a relationship between dp2 and dp1? Yes, we do. So let's substitute for dp2 with this equation. So dp2 equals 2 dp1, and therefore we get a relationship between the new beta naught and the old beta naught to equal half. Okay, good. That means beta naught 2 equals half beta naught 1, correct? And therefore alpha 2 case 2 is also half of alpha 1, right? So now we have a smaller value for alpha. And remember, we said when you have smaller value for alpha, that means you'll get lower pressure drop. So we explained it using the logic. Now we are explaining it using the equation, but of course the logic is the most important explanation. Okay, so lower alpha. Let's go back to the resulting design equation here. Solve the evaluated equation of the design equation and solve for x again and get x to be 77% conversion. Obviously, it's higher than the previous case, correct? It's higher than the previous case, which was around, I think, 69%. Sorry, it was 69%. Now we have 77% because I have reduced the pressure drop in my reactor by increasing the particle size. So we get higher conversion, but of course, still the conversion is lower than what we could have got if there was no pressure drop, which was around, I think, 82%. Was it 82%? Okay, but of course we cannot avoid pressure drop totally because we have a packed bed reactor. طيب, I'll leave you with 3 questions that you should think about. Actually, the answer to these questions are kind of provided, or you are guided through the answer of these questions and the complete set of slides. So let's see what these questions are. Question 1, how your answer to B would change if the reactor diameter was increased by a factor of 1.286. That means I have changed the pipe from 1.5 inch to 2-inch scheduled pipe. So how that would change X? Obviously you're thinking, if I increase the diameter of the pipe, I will reduce the pressure drop and I'll get higher conversion. Yeah, you're right, but go through the details explanation and see how that will affect the equations. Question 2, does changing the catalyst particle size dP affect the porosity? We said it does not, but please prove to me. And again, the answers given, all you need to do is to reflect upon the equations. Question 3, for a porous catalyst, does changing the catalyst particle size affect the surface area? So again, we are talking here about porous catalyst. What does porous catalyst mean? It means a catalyst where its surface area is not coming from the external surface area. The surface area is coming from the internal surfaces inside the pores. So if I change the catalyst particle size, dP with the surface area change. Okay, so I'll leave you with these 3 questions. Please go ahead and reflect upon them and answer them at home. It was good to talk to you again, and we'll meet inshallah on the next lecture. Bye for now.